On the front of the Bomem here, we have two different detectors. We have a silicon detector that's good from 50,000 wave numbers down to 8,500 wave numbers. And then we have an indium antimony, or InSb detector, that's good from 12,000 wave numbers down to 2,200. Now, 50,000 wave numbers is way up there. This is right on the edge of far ultraviolet. And 2,200 wave numbers is way down there. This is right in the middle of mid-wavelength infrared. So with these two, we can detect most of the ultraviolet spectrum, all of the visible spectrum, all of the near-infrared spectrum, and about half of the mid-infrared spectrum. That's an incredibly wide range, but we have a bottleneck elsewhere in the system, and that is the beam splitter. The beam splitter that's in this one is an IMB21, and you can see that it's good from about 20,000 wave numbers down to about 4,000 wave numbers. If we wanted to push into the ultraviolet, we would have to change out to the IMB34 beam splitter. Mike has one of those, and I'm definitely going to borrow it, and we're going to play with the ultraviolet on this machine at some point in the future. And if we want to get further into the infrared, we have to get a KCL or a KBR beam splitter. And the KCL is incredibly rare. We don't know anybody that's got any of those that's willing to let us play with them. And the KBRs are incredibly hygroscopic. I think that's the right word. They love water. They love moisture. So they absorb moisture and they just kind of destroy themselves. So those are also now getting quite rare. So getting into the mid-infrared and far infrared is a kind of your princesses in another castle type of quest that we're going to deal with on a different day. However, with these two detectors, we can make full use of the IMB21 beam splitter that we have in this machine, except that this InSb detector here is not mine. This is Mike's, it's on load. I'm gonna have to give it back at some point in time. And to make matters worse, it needs liquid nitrogen to work. You have to fill it with liquid nitrogen to keep it incredibly cold so you can get the sensitivity out of it. But I don't have a dewar and I don't have any liquid nitrogen. So for the time being, we're kind of stuck with the silicon, which feels very limiting. And I was lamenting a little bit about this over on the Discord, and my good buddy Tician chimed in and said, hey, I've got some photodiodes that I would love to send you. So I said, absolutely, bring it on. And Tician didn't just send some photodiodes, they sent the most amazing care package ever. It was full to the brim of cool old electronics, power supplies, and a boatload of photo multiplier tubes. I love PMTs. I think they're just gorgeous, but also I think we can build something really cool with these, and so we're definitely going to do that. Tician, thank you so much for the care package. I'm completely blown away. But in the middle of all those PMTs was this little guy right here. This is an Indium Galium Arsenide photodiode, and it has a wavelength range of 12,500 wave numbers down to 3,850 wave numbers. That is almost identical to this InSb detector right here, only this photodiode doesn't need to be cooled by liquid nitrogen. It doesn't go as far into the infrared as this InSb does, but that doesn't matter because we don't have the correct beam splitter to go that deep into the infrared anyways. So this is going to be excellent paired with that silicon photodiode that we have on there already. The only problem is that I can't use it like this. I need some way to mount it. I need some way to seal it so that way we can pull the whole system down to vacuum. And I also need another mirror to steer the light into the detector. And so I've got an extra little box right here that has the mirror that we need in it. And so I need to machine up a slug that goes into the top of this box and that holds this photodiode perfectly in the center, sealed up. And then I need to run some wires out of it and over to a preamplifier. So I've got a giant chunk of aluminum over here that we're gonna slap into the lathe and try to machine down to something that'll work. This could be a complete disaster, or I could come out looking like a rock star. I have no idea how it's gonna go, but the only way to find out is to start making chips of aluminum and see how it goes. I'm really happy with how this turned out. I mean, it's always nice to hold like a massive machined chunk of aluminum in your hand. It's really hefty. But we can see that I got my detector right in the center, properly isolated from the rest of the aluminum via this rubber washer that's all epoxied into place. I did make a couple of mistakes though. On the top here, I used way too fat of an O-ring. So I went and bought a skinnier O-ring and swapped it out, and that O-ring was too skinny. So I ended up back on the fat O-ring, and you can see that like the top plate here is a little lifted off, but it is making full contact with that O-ring. And honestly, I don't think it's gonna matter that much because that's not even the primary seal against vacuum. That's gonna be down here with this rubber washer that's all epoxied into place. That should be what prevents atmosphere from being pulled in whenever we pull the system down to vacuum. This is just kind of like a secondary stopgap. But other than that, I mean, it is a pretty simple chunk of aluminum. It's just machined really well, and it slides in absolutely perfectly. Now all we got to do is plug it into a preamp, get it on the machine, and start testing it. But there's a bit of a problem there. This is the InSb detector that I have sitting here on the desk, and here's the preamp bolted to the side of it. Now, I have no idea why Bomem did this, but instead of making it so that the detector plugs into the preamp, they make it so that the preamp plugs into the detector. And that makes no sense because the preamp is kind of a universal thing. They set it up so that it can be used with multiple different detectors, but then they solder a wire that's unique to the specific detector you're using. So if I want to use this preamp with the new detector that I made, I'm going to have to desolder the wire from it and solder my new one onto it. And that makes it really hard to kind of bounce back and forth because now we're in a situation where I've got 3 different detectors in the room, but only 2 preamps. So I could, of course, call Mike and ask him to send me another preamp, but there's only a limited number of these preamps, and if I'm making new detectors, it sure would be nice if I could also make new preamps. Now, this preamp board here looks pretty simple. It is using older metal can ICs, but these are just like run-of-the-mill op amps, OP16F2 and LM310, and we found that TL081 and TL082 are pretty much equivalent to those. Everything else on there is Jelly Bean with the exception of this IC right here, which is an MN2020. This is a digitally programmable gain amplifier. Essentially, you can send in a 3-bit binary signal, and that is interpreted to change the gain of the amplifier into one of 8 different levels. Now, this MN2020 is no longer being produced, and that created a bit of a problem, but it turns out that programmable gain amplifiers are still a thing and they are still out there. So the PGA281 programmable gain amplifier is the closest thing that I could find that was still in production, and the primary difference between it and the MN2020 is that the MN2020 takes 3 bits in and the PGA281 takes 5 bits in. So if I want to use the PGA281 with the Bomem, I'm going to have to do something to the binary values that are coming in from the Bomem and change it. So I asked around a bit on the Discord, and somebody had a really brilliant idea. Thank you so much for this. Take the 3 bits from the Bomem and send them into a 4-bit binary adder to add the value of 0011 to them, and then that changes that 3 bits to the correct value going out into the PGA281, so that way whatever the Bomem sends ends up with the correct amount of gain going into the PG281. It's like really clever way to solve that problem. And so I came up with this little schematic right here. And I came up with a layout that I was pretty happy with, and I logged on to PCBWay and JLCPCB to see if I could order the boards. The board cost was essentially nothing, and then shipping was $95. It was like 45 bucks of shipping, and then because I'm in a rural area, they had a $50 surcharge. So yeah, I'm not using JLCPCB or PCBWay again until that shipping price comes down. But that then, like, what am I gonna do for getting my PCBs made? Normally I machine my PCBs, but the PGA281 is only available in a surface mount package. Like, that's just so small. I tried to lay it out and machine it on our mill, and I just don't have the RPM. Like, I tried to use a 20-degree V-bit. Every time that V-bit touches the copper, it just breaks the tip of the V-bit. So I can't machine it unless I get like a 10,000 RPM attachment for our mill. I'm certainly not going to do that. So I decided to give Oshpark a shot, and their board cost was a lot more expensive. It was $45 for 3 boards, which is pretty crazy when you think about, you know, what the comparison is to the Chinese companies. But well, shipping was free, so here I am with some Oshpark boards. It came out to be half of the price of ordering from one of the Chinese companies, and honestly, I'm pretty happy with the quality. So I just need to solder one of these up, bolt it to the side of the detector here, get this onto there, fire everything up, do a whole lot of alignment because I got to get everything optically aligned correctly, and then we can start taking this thing for a test drive. After bolting everything in, I gave the machine a power on, and you can't quite see it in this clip, but the new preamp let out a small wisp of smoke and immediately killed both the plus 24 volt and minus 24 volt rails. Whoops, I must have something horrifically wrong on my preamp board. Fortunately, it only took out the fuses, everything else was all right. So let's swap back over to the original preamp board for now. Then I'll slot the new detector slug into place, and it has a really nice tight fit with the sealing O-ring in the box. To make sure that I get the vertical alignment of the detector slug correct, I need to pop a little light chopper into the sample compartment. Then I just fire up the scope on test point 1 of the preamp, and I adjust the height of the detector until the chopped signal on the scope shows the highest value. It's pretty easy to get it set just right. And looking at a basic interferogram, it looks wonderful, except we actually have too much signal. You can see it clipping at the peaks. That just means that we don't have enough attenuation in the filter wheel, so I'll pop in a few more steel mesh filters to bring the intensity of the light down a bit. Then it's into the PDP-11 software. I need to tell it what the spectral range of the new detector is and which filters to use. Then, to make sure it's all working as expected, I'll just take a quick phase measurement. The mirror goes up and down, taking multiple interferograms, and we get this excellent looking spectrum out the other side. There are a couple of big dips in our otherwise smooth curve. The big one at 4000 wave numbers is actually the quartz of the beam splitter and detector lens. I'm not entirely sure what this one over here on the right is, but it could be a water absorption peak since we're still at atmosphere. And this messiness at the top is really interesting too. I would guess this is also water absorption in the atmosphere, but man, I really need to get this thing down to vacuum. No clue what happened to my homemade preamp here. I'm gonna have to sit down and just like troubleshoot this later. It's the classic case of me trying to do too much in too short of a time. I just get excited and I can't help it. But in this case, getting excited resulted in a little bit of magic smoke, and so we're gonna have to sit down and like properly troubleshoot this. Well, we've got the original preamp in there, and it does seem to be working fine. I've already gone through and I've done the define, the phase, and the setup. So let's actually take a measurement of my favorite thing, ethanol or Everclear. But we're gonna start with a reference. And so I've just got an empty cuvette in there right now. And so we'll just go ahead and hit enter on this. Brings up the whole big menu here. And we're gonna use the setup file of QZ3QU1. We're doing ethanol from 12K to 4K. This will be the third time I've done this. Spoiler alert, this is like, I tested this out before I turned the cameras on. Sometimes that's how filming goes. We're going to be doing from 4,000 wave numbers to 12,500 wave numbers. That is the full range of this Indium Gallium Arsenide photodiode. We're taking 10 scans at a resolution of 1.5. So I'll just go ahead and hit enter on this. And it's going to take 10 scans to get a kind of a baseline of what's in the atmosphere, what the composition of the glass is, and it's going to use that baseline to kind of subtract away from our actual measurement. So that way we're really only looking at the substance itself. There we go, remaining scans 1 out of 10. Transferring data from VP to host. This takes a little bit. Whenever you do a scan at a resolution of 1.5, that's a pretty big file. I can see that the MFM drive down there is working hard at it. All right, now we could display that, but there's really no point. It just ends up looking like a flat line. So what we're gonna do is come down and do a transmittance, and I'm gonna hit enter on it, and it's gonna bring up a bunch of the same stuff. So we're going to do 12K to 4K003. That's going to be our transmittance file that comes out. Sigma min is 4,000. Sigma max is 12,500. It's all the same settings from the previous menu. But now I need to pull the empty cuvette out and put in the cuvette that has ethanol in it. All right, now we just hit return on this screen. It's gonna, looks like it's gonna pull us back to the main menu, but if we look up in the top, that's where all of our information is. Remaining scans, 10 out of 10, 9 out of 10, it's gonna count down, and then it's gonna calculate the FFT, and once it's done transferring data from host to VP and VP to host, it's, well, then we can look at it. There we go, we got it ready up there, so I'll just go ahead and hit display. It automatically fills in the name for us, E12K4K003. Sigma min, Sigma max line up with what we told it to test. So we'll just go ahead and enter on that, and it should display the spectrum of ethanol. Yeah, look at that. Oh, that is super cool. Because at this point, we're essentially doing real deal science. This is the type of thing that this machine would have been used for when somebody was using it in anger back in the day. But the really cool thing here, and the reason that I chose to look at ethanol again, is that the last time I was looking at ethanol with this machine, I was stuck with the silicon photodetector. And so I was only able to really look at just a tiny portion of the interesting bit. Because once you get into the visible, ethanol is like totally transparent. It just like passes absolutely everything. I mean, we can tell this with our eyeballs. We hold it up and it's like perfectly clear. And so I was comparing the little bit of near infrared that we could get out of the silicon detector with a known spectrum that's over on Wikipedia on the near infrared spectroscopy page. And the person who created that spectrum chimed in on that episode. It was Muonium 1. I'm not sure I'm pronouncing that correctly. I'll show the comment. But it was so cool. It was just this starstruck moment for me to like interact with somebody who has something that is on Wikipedia that I have used as legitimate reference, and I think is a fantastic reference for everyone who reads about spectroscopy, particularly in the near infrared range. And so I wanted to take another spectrum of ethanol in the near infrared to mid infrared range, which is what we've done with this indium gallium arsenide. And if we compare this output with the output that's on Wikipedia by Muonium 1, they match perfectly. Now the scales are flip-flopped because I'm looking at it in wave numbers, and Muonium did theirs in nanometers, and so my right side is going to be their left side. Also, the vertical scale looks a little different, like our peaks are lining up in quite different intensities, but the peaks are all in the exact same places. Like I moved my cursor around to check. This big low peak right down here is at 8,400 wave numbers, and that lines up perfectly with the nanometer peak that's shown on theirs. The same with this tall peak here, and then when we drop down here. Now, the one on Wikipedia seems to peter out at about 6,000 wave numbers, which is right, this tiny little blip right down here. And I've got a whole lot more resolution beyond that. I've got a full 2,000 more wave numbers beyond that. And there's not really a whole lot exciting going on there. And actually, I mean, this is quite interesting in general if we look at this whole left side of my screen here, because from 4,000 wave numbers all the way up to about 7,000 wave numbers, like ethanol is completely absorbing all of the infrared energy that's hitting it. So for something to be so totally transparent to our eyes, I mean, this is crystal clear. Looks like it's not even there when I'm looking at it. When we get into the infrared range, particularly the near infrared to the mid infrared, it just absorbs it all and doesn't pass any of it. That is absolutely fascinating to me. So we had a swing and a miss with our homemade preamp, but we completely knocked it out of the park with our homemade detector here. This is really exciting. It works better than I could have ever expected, and it honestly fits the aesthetic really well too. I'm super happy with how this thing turned out. I just noticed it says DTGS 10 to 700 on here. So originally it had a far infrared DTGS detector in this box, but obviously I don't have that detector, so I'm gonna have to replace that label. But what do you call those? Is that like a Dymo, I think, right? D-Y-M-O, Dymo, I don't have one of those. I'm gonna have to get a Dymo punch. And then I'll peel that label off and I'll put INGAAS on there and then list out what wave numbers it can go to, because like, I'm never pulling that out of this box. It works way too well for that. We do have a couple of more problems aside from our preamp issue, which I'm going to sit down and troubleshoot this, because I really do want to get this, preamp of my own design on the side there. But my laser, oh hey, it finally went stable. My laser takes forever to go stable, and sometimes it just doesn't turn on. So the laser is getting more and more unstable, more and more unreliable. So at some point in time, I'm going to have to replace the laser tube in it. Heaney laser tubes have a lifespan, so that's going to have to happen. And when that happens, the alignment procedure for that is like a proper battle. So that'll be a fun one to experiment with. And then if we really want to start using this machine in anger like it's supposed to, we absolutely have to get it down into vacuum. Now I have a vacuum pump for it, but I also have to water cool the sources, otherwise they'll just like immediately overheat in the vacuum. So I've got to figure out how to run water into this room. I think I'm just going to do it with like a wastewater setup where it comes out of the faucet through the machine and then spews back out into the yard. I'm not using the thing every day, so I think that'll be fine. So there you go. That's the roadmap for the Bomem, but hey, I'm really excited with how this thing turned out. I'm going to sit down and play around with it for a little bit more. So I want to thank you all so much for hanging out with me today, and I hope to see you in the next one.